In section 4.2 on determinants of order n, there is an important lemma, and a lemma is like a theorem except for it's really a building block upon which other theorems and results are built. So here's the lemma. Let B be an n by n matrix of size greater than or equal to 2. If row I equals the kth identity vector for some k, then the determinant of B can actually be written as -1 to the I plus k determinant of the ik minor of B. So the book has a proof of this, but I think the most challenging thing for me is just to make sure you understand what's actually happening here. So what does this actually mean? So can you see how this matrix here, the fourth row, is one of the canonical vectors, right? Okay, so this theorem is saying the determinant of this, you can just think of it as 4 down, 2 over, so -1 to the 4 plus 2, determinant of the minor of this element, which includes that column, and that column. Make sense? Okay, so the book has a proof of this, but I want you to understand sort of what's really happening in the proof, because when you're in a proof on that uses induction and uses matrix subscripts, and this uses 2 sets of subscripts, it can be easy to lose track of what's happening. So here's how the proof works. Let's imagine you had a matrix like this and you're trying to take the determinant. Well, right now we just have the definition of determinant. So we are going to do the expansion along that first row. So 1 times the determinant of the minor related to the 1, 1 entry, -2 minor related to that entry, and so on, +3 minor related to that, -4 minor related to that. Now here's where the proof can get tricky. What they say then is, well, then let's do that process by induction. So let's assume that it was true for all 3 by 3 matrices. Then you can take this matrix and say, well, that was really just the right number of -1s times that minor, right? So now you start here, but you're now 2 levels smaller, the minor of the minor. And similarly here, this one, since it has a row that's entirely 0, you're going to get 0, and similarly here, you get that minor and that minor, and it can be a little tricky because you don't just sort of truck right along with these canonical vectors, because when you're to the left of the row you're omitting, you do something different than when you're to the right of the row you're omitting. Okay, so notice you get this, and then you're like, wow, that's quite a complicated result. But then they pause and they say, but hold on a second. Think about, we are actually trying to prove that it's equal to this. Think about how you would actually calculate this. Well, you would actually calculate this by doing the minor expansion across the first row, and that's exactly what we have there. So we did an example. Theirs is a full proof, but I think having some sense of what the example is really helpful for the proof. Okay, but before I go on, there's a key implication here, and you can take the implication from a number of places in the chapter, but this is really important. Upper triangular matrices, you can take the determinant by calculating the product of the diagonals, and you can actually see it from this result. So let's imagine you had something that was all 0s down here, right? And then you had 2, 4, 6, 8, 10, 12, 14, and then whatever entries you wanted up here, right? Well, why should you believe that it's actually the product of these entries? Well, because you can take this bottom row, right? And we already proved that by the first theorem that this bottom row is equal to 14. The determinant is equal to 14 times the determinant of this. But what's the determinant of this according to the lemma? Well, it's equal to -1 to the n plus n, that's even, so that disappears, times the determinant of this. So you've got 14 now, times the determinant of this. But by that same first theorem, you can take 12, and it's times the determinant of this, times 10, and so on. So if you can get an upper triangular matrix, it's really easy to take the determinant. You just basically read it off as the product of the diagonals.